Are you ready?
Yeah.
So this afternoon I will talk about unification in description logic, and also probably there will be time we will start to evaluate unification type in some modal logic. So description logic is a very important topic in artificial intelligence knowledge representation. There is a lot of paper, chapters, handbook, etc. And its syntax, there is different language, description languages, and most of the time, except in some cases when there is additional constraint, most of the time the language of description logic are fragments of the language of multimodal logic. For example, the language FL0, one of the most popular, is a fragment of multimodal logic in which there is the constant true, conjunction, and boxes. So here boxes are not denoted by squares together with a parameter, they are denoted in this way. R is an abstract term denoting some accessibility relation, but of course in the syntax R is just an abstract symbol. But we can consider that such a language corresponds to the fragment of multimodal K when we have only true, conjunction, and boxes. So we are talking about concepts and roles. Concepts are formulas, they are denoted by such letter. There is atomic concept, and roles correspond to boxes. So an interpretation is like a Kripke model, but the way to present them is a little bit different. So there is a non-empty set, the domain, and there is a function which interprets like a valuation, but also the accessibility relation, which give an interpretation to every atomic concept, and also interpret every role by a binary relation on the domain. And the interpretation function can be extended to any concept in the expected way. True is interpreted by the full domain, conjunction is corresponds to intersection, and the interpretation of such concept, the boxed formula, is interpreted to be the set of all elements of the domain such that every element E of the domain which is accessible from D by the interpretation of R belongs to the interpretation of C. So we have just a fragment with true conjunction and boxes of multimodal K, and the main decision problem in this setting is given two concepts. People were interesting to define algorithms to decide if two given concepts are equally interpreted in all models, or if one concept subsumes another concept. It means in all interpretation of all models, the interpretation of C is included in the interpretation of D. For the language FL0, this problem is solvable in polynomial time. Okay, but we want to do unification. The unification problem in description logic has been motivated and studied first by Franz Bader and with different other people. So, since we want to do unification, we want given two terms to determine if they possess equivalent instances. We have to separate the set of all atomic concepts in two categories. Atomic concept variables and concept constant. Because otherwise, if there is no variable, there is no unification problem at all. The unification problem consists to find the appropriate substitution, which will make two things equal. If there is no variable to be substituted, there is no unification problem. So in the setting of unification in description logic, FL0, we have the same syntax, except that here we have two kinds of atomic concepts, constant and variable, or parameter. We can consider that constant are like parameter. Rybakov, in his book, is talking about parameters. So we have the same language, and of course in the interpretations, the interpretation function, not only it has to interpret every atomic concept constant by a subset of the domain, like the valuation in a Kripke model, but also the interpretation has to say what is the interpretation of every atomic concept variable.
I have a question. What, is there a simple reason why do we need to consider atomic constants, not only variables? We didn't do so for modal logics. We had only variables.
In modal logic, I have not been so explicit. Maybe I have been such explicit. I have said there is two kinds of unification problem. The elementary unification problem, it consists, given a formula without parameter, to determine if it possesses a unifier. If it can be instantiated, and the instantiation to be valid in the logic. And there is unification with parameters, or unification with constants, and it is the following. Given a formula which contains constants or parameters, try to find a unifier. For example, in classical propositional logic, if I give you this formula, x implies a, now this is a variable, and this is a constant. Then a unifier of this formula, for example, is a substitution which replaces x by a. Another unifier can replace x by false. And if you do either this one or this one, then the given formula will become a tautology. But it is not permitted to replace a by x, for example, to obtain x implies x, because parameters, constants, cannot be substituted. Most people, like Ghilardi, for example, Silvio Ghilardi, is saying the following. He is developing tools and techniques to show, for example, that some modal logic is finitary. But he's considering the elementary unification problem without parameters. And he said, oh, my tools and my techniques can be easily adapted to the case when there is parameters. And in this case, it is true. But there is a situation for which elementary unification and unification with parameters have different complexities and also different unification types. It is possible for elementary unification to be unitary, for example, and unification with constant to be finitary, even in the same logic, if it is the same logic. But in the case of description logic like FL0 and EL, elementary language, Franz Balder and his group then consider systematically a language possessing those kind of atomic concepts. So I am following their perspective. Yes, this is the interpretation of concepts in some way. Now, a substitution, as I have just said, a substitution is a function which associates to every variable some concept description. So it is like in modal logic or classical logic, a substitution is a function, sigma or tau, which associates to the variable of the language some concept. And of course, it is possible to homomorphically extend this function by this way. There is an example, I think, just after. And we will say that a substitution sigma is a unifier of two concepts. Here we don't unify a concept alone, because it is meaningless to say, oh, I will unify the concept C. What does it mean to unify the concept C? In the language, there is just conjunction and boxes. Unification problem is a pair of concepts, or a finite set of pairs of concepts. And A unifier of such a pair, C and D, is a substitution, sigma, which, when you apply it to C and D, makes C and D equivalent. Here, the equivalent is equally interpreted in all mod Kripke models. Okay, and then we say that the concept description C and D are unifiable if they have such unifier. For example, if C and D are these two concepts, remind that this denotes a box. This is a box. This is a box. So here there is two boxes, but they are different boxes. A is a parameter. It cannot be substituted by something else. And here x and y are the variables. There are different concepts, and it is possible to find interpretations in which C and D are differently interpreted. But if we apply to C and D such substitution, sigma is the substitution replacing the concept variable x by this concept, and the variable y by this one, then what we obtain is relatively simple. When we apply sigma to C, we obtain this part remains unchanged, and for all R, x is displaced by A intersection with all S A. And then when we apply sigma to D, y has been replaced by this one. So we have this one, this one, this one here. The intersect here it is but this box distributes of course over the conjunction. So for all R, for all R A, we have this, that we have here. For all R A, we have here, and for all R, for all S A, we have here. And so modulo the associativity, commutativity, and the distributivity of the box over the conjunction, the two concepts we obtain are equally interpreted, so sigma is a unifier.
In this example, you substituted for variables some concept expressions that involve only constants, not variables. Is it essential?
If there is, it is possible that the substitution, for example, sigma x, to contain occurrence of x, y, and other variables. There is no such limit. But if there is a unifier of two concepts, such that sigma x or sigma y contains variable, then there exists another unifier which is variable free, that is to say, which is of that kind.
And this related question, do you consider finite alphabet of A's and or countable? And this there is a difference for this problem, because in description logic they usually consider finite set of concept names, finite set of role names.
No, I
if you restrict substitution of
consider infinite sets.
Countable
infinite countable, yes.
Okay.
I don't know what is happening if
because the complexity of some description logics depends. Do you have infinitely many role names or finitely many role names?
Yes, I know. But
and similar for concept names.
The concept of unification, I think they consider only a countably infinite language. Well, both variable and parameters are infinite.
Infinite.
Okay. Okay, Jeff, this is exactly this. Thank you for your remark. A substitution is ground if, for all variable x, sigma x does not contain a variable. And this is exactly your question. Because of the rule of uniform substitution, if two concepts are equally interpreted in all models, then any instance of these two concepts by the same substitution are also equally interpreted in all models. Yes, I can skip this one. There is no need. This is interesting property, not in fact not so difficult. If we have such concept, NC concept and ND concept, and if we have roles, n roles, pairwise distant, it is important they are pairwise distant, then these two, the two lines are equivalent. So the first line is saying that C1 is equivalent to D1, etc. Cn is equivalent to Dn. And the other is saying that, so here we have n equivalence, and this equivalence is equivalent to only one equivalent, where on the left and on the right, each C is prefixed by a different box.
And this is the first time in your lectures where it is essential that we have many modalities instead of only one. We couldn't do the same in unimodal logic.
Yes, but concept language, description language in which there is only one role, I have never seen. Maybe we can assume, but
in standard ontologies you only have one, it has a fixed number of roles. You don't have an arbitrary many roles.
Yes. But this lemma is just to say that if we want to solve the unification problem consisting of n equality, we can, in fact, it is equivalent to have a unification problem with only one equality.
Given that we have infinitely many.
But it is easy to have infinitely many, potentially a lot of boxes. So the first line implies trivially the second line, and the second line implies the first line because it is also very simple. Suppose that this intersection is equally interpreted to this other intersection. And suppose that there exists E or G such that CG is not equally interpreted with respect to DG. What does it mean, this one? It means that for such a G, there exists a model, there exists a Kripke model, in fact, and there exists in this, so this is my Kripke model, and there exists a possible word in this Kripke model, that is to say, an element of the domain, which, for example, satisfies CG, so I will put plus here, but does not satisfy DG. I put plus and minus because there is no negation symbol. Okay, this is what it means. For example, in this order, or the converse, CG is not satisfied here, but DG is satisfied. Okay, and now this is the situation. Now let us consider the generated model starting from this point by means of the accessibility relation. And let us consider an extension of the model by putting here an accessibility between a new point and the root of this one. And let us interpret this by RG. And so here, this one is true. This point satisfies this conjunction. It satisfies this concept for all E different from G because there is no RE accessible point. And it's accessible the RG CG because the only accessible point satisfies CG. So this point satisfies this intersection, but of course it does not satisfy this one because it does not satisfy for all RG DG. It does not satisfy for all.
And it was not essential that we are talking about FL0 concepts.
Yes,
it's the fact about K, multimodal K. Or
it is essential because if there is, for example, tense modality,
well, tense modalities are.
You will be, or universal modality, it will not be possible. Yes, it is essential to make some assumption about the language. Okay.
It's not about the fact about the fragment of multimodal K, it's the fact about the K, multimodal K itself.
Yes, yes. Okay. And now let us consider the unification problem. But before, I want to talk about finite sets of finite words over a finite alphabet. An equation between expressions determined over such finite sets. So here I have, it is written an equality. So there is n variable and the same variable on the other side. And there is S0, S1, Sn, etc., T0, T1, Tn. And this S and T denote finite sets of finite words over some finite alphabet. For example, if our alphabet contains the letter R and S, then the S set and the T set will be any finite set of finite words over this one. And this symbol represents the concatenation between two finite sets of words. Variable, we are looking for some value that we will give to this variable in such a way that the set on the left is equal to the set of words on the left is equal to the set of words on the right. So x represents variable that we should give to them the value to be finite sets of finite words. And this is concatenation between two sets. This is standard union. For example, this is a possible equality like this. This is another equality like this. We have seen maybe last week what is the solution of this equality. One possible solution is to replace x by the finite set of finite words, which consists of the empty word, denoted like this, and the word S. Yes, S. And if it is, what is equal the left part? It is equal to the finite set of words consisting first of the word R plus of the concatenation of RS with the empty word, that is to say RS, and the concatenation of RS with the word S, which means RSS. So the left part, with when x is equal to this one, is this set of words, and we can compute the right part, it will be equal. Now, why I am talking about equality to solve equation between expression like this? Because it is possible to reduce the unification problem between two concepts to the problem of solving such equations. So, suppose that we have two concepts C and D, and they contain some variable x1 to xn. And suppose they also contain some parameter, constant, a1 to ak. So, you will accept easily that it is nice to abbreviate a sequence of boxes, to abbreviate like this. And doing this one, and of course we want to say that this universal quantification followed by a sequence of role names will be interpreted in description logic models like this. But here, immediately, we recognize a finite word over the alphabet consisting of all role names. And therefore, using the associativity, commutativity, idempotence of the conjunction, using the fact that conjunction has a unit which is the Boolean constant true, it is possible to rewrite the concept C and D in this way, like a kind of normal form, conjunctive normal form. A1 is preceded by some set of things like this, because if we have, for example, for all RS A1 intersection for all S R A1, we will represent like this for all RS SR A1. To say that A1 is the box which are before A1 are the RS and the SR rows. And we do this for all parameters and also for all constants. So it is relatively easy to associate to C and D such conjunctive normal form, where the S here and the T there are finite sets of finite words over the alphabet consisting of all whole names. But there is another property which is also very simple to show. This time, suppose that they are ground, there is no variable. And suppose that C and D have been written like this. So here U1 and V1 are finite sets of finite words of that kind over the alphabet of all whole names. Then, so they are ground, there is no variable in C and D. Then C and D are equally interpreted in all models, if and only if all corresponding pairs of sets of words over the alphabet of whole name are equal. U1 is equal V1, etc. K is equal to K. It is easy to prove. The proof is similar to what I have proved before. And now we are ready. Well, we are ready. Yes, it is this result to reduce the unification problem in the concept language FM0 to the problem of solving equations of that kind. So the theorem says the following. Given two concept descriptions C and D, based on the variable x1 to xn and on the parameter a1 to ak, and suppose that C and D are already written in their conjunctive normal form. So here we have sets, finite sets of words. Let us associate to the pair C and D k equation of that kind. K is the number of parameters in the concept. And each equation, so for example for such integer, consists of how it is obtained. That part is the same as that part. And that part is coming from the parameter AI. So it is the whole quantification before the parameter AI, and the same on the right side, but this time with respect to D. Let us see an example. It is not difficult to show this theorem. I will try to show. Let us see an example. Suppose we are given these two concepts. So there is two parameters, A1, A2, two role name, R and S, and one variable. There is only one variable, x1. The conjunctive normal form of C and D are like this. Here A1 is the singleton R because A1 is just interested by R. A2 is the singleton RR because it is RR here. And x1 RS because of this. In D prime, A1 corresponds to RSS because of this sequence. A2 corresponds to RSR RR because of this together with these two, and this pair. And X corresponds to RT. So we have written C and D in conjunctive normal form. And then, since we have two parameters in this concept, we associate to the unification problem between C and D two equations of that kind, and the theorem says that C and D as concepts are unifiable if and only if it is possible to solve the first equation and it is possible to solve the second equation. It is not a system of equations, they are separated. Let us try to solve them. Oh, but maybe we have done before. I think it is the same equation as, let me see.
Empty and S.
Empty and S. So
X1.
x1 will be interpreted by empty and S. Yes, it gives a solution. And the x12, I think it will be R. R is a solution. It will be RR, RSR, and here RR, RSR. So the two equations have a solution, independent solution, and therefore, according to the theorem, these two concepts are unifiable. Okay, how do we prove the theorem? There is two directions, of course, because it is an equivalence. Which one is the... Yes, suppose C and D are unifiable. So suppose sigma is a unifier, and we can consider it is ground of C and D. Also, we can consider that sigma of x1 contain only the parameters these parameters. In fact, it can also be proved that if two concepts are unifiable, then there is a ground unifier of them, such that the parameters occurring in this concept are exactly at most the parameter occurring in the unification problem. Okay, and now let us interest one of these equations. Let us interest one of these equations. Because sigma is a unifier, it means that I will not write, yes, like this. It means that this intersection which corresponds to that part, intersection with the big intersection for all variable sigma of x g is equally interpreted in all interpretation to this intersection. Okay. Now, so if sigma x is a, you can see it as a conjunction of if sigma x, we can see it as a conjunction of the form of this form, some finite set of finite words. If sigma xg is a formula of that kind, because we have said that sigma xe contains only those variables. So sigma xg can be put also in such conjunctive normal form. Now, so it means that here we have a long conjunction of boxed parameters here and there. This conjunction of boxed parameters, let us see them as modal formulas. And if we choose one arbitrary parameter, for example, A1. If we choose, for example, the parameter A1, and suppose we replace all other parameters by the constant true. It will not change the equality, the equivalence, because by the rule of uniform substitution, if you replace all parameters from A2 to AN by true, then it will still be equally interpreted. And so by isolate, you keep in this long conjunction just that part corresponding to A1 and eliminate all of them. So here you will have S0 you will have the set S01 corresponding to A1 here. The other set corresponding to A2, A3, they don't exist. But here we have SV for all G, so from S1 to Sn with UI. U1 corresponding to A1, union, etc., union Sn concavity to Un, and this set is equal to, it is U here, T1, U1, etc., union Tn, Un. If sigma is a unifier, and if sigma is variable free and does not contain any other atom than A1 to AK, then this long conjunction is equivalent to this one. Replace all parameters except A1 by true. It means that it implies that the union of these sets of finite set of finite words are equal. And therefore, what it means that this equation between finite set of finite words has a solution. And the solution is to replace x1 by this one and xn by this one. Okay? So we have proved that the unifiability of C and D implies that each equation of that kind is solvable. The other direction is the same. And we are using the fact that the language contains only top, conjunction, and boxes. So it shows the equivalence of the unification problem in FL0 and to solve such equation in the case of finite set of finite words. And the complexity, it has been evaluated by Varder and Barenbrant. They have proved that this, to solve such linear equation can be done in deterministic exponential time, and therefore the unification problem in FL0 is solvable in deterministic exponential time. There is also the language EL, which is very popular, but I think I will skip. So EL, let us see quickly. It is a very popular also concept language, and it is almost the same as FL0, except that here we have diamonds instead of boxes. And of course, the models are the same, and the interpretation of concepts are the same, except for this one, which corresponds to the diamond multimodal logic K by existential quantification over some accessible element of the domain. again, and for this reason, this concept language are very interesting because both the problem of concept equivalence and the problem of concept subsumption are solvable in polynomial time. This is a quite old property. And now it is possible to ask what is the difficulty to find unifier of two concepts C and D. Exactly the same definition, what is a unifier and what it means for C and D to be unifiable. For example, this C and this D are unifiable. For example, if we replace X by top and Y by anything, it does not matter, or maybe Y we don't change, sigma X equal top and sigma Y equals Y, for example, it will be a unifier of these two concepts. It has been proved that unification is NP complete, and it is of Mullary type. Mullary because the previous example, these two concepts are unifiable, but they don't possess a minimal complete set of unifiers. And in fact, the proof that the unification problem consisting of these two concepts is Mullary. It is solvable, but there is no minimal complete set of unifiers. It is very similar to the proof that K is Mullary. And since we will see the proof that K is Mullary, I don't insist.
So we have two fragments of multimodal K in which the problem of unification is decidable and quite easily decidable polynomial.
No, for FL0, deterministic exponential time.
Exponential, which is better than undecidable.
Yes. I was not able to find what is the unification type of FL0.
And for K itself, it is unknown.
The computability is unknown, and the type is known to be Mullary.
Yes.
And this is one of the part of the following topic. Now we will, if you interest in the unification problem, well, even if you, given a logic to determine if the unification problem in this logic, either elementary unification or unification with constant, is decidable, either it is, I mean now, after all the work done by Rybakov, Pilardi, and others, it is relatively easy to say, oh, this logic has decidable unification type, or this logic it is undecidable. Because the remaining unification problem, either it is easy or it seems very difficult. For example, for modal logic K, it is an open problem. So maybe it is not so interesting to attack such problem first. First, I think it is more interesting to make a practice to try to determine the unification type of such or such modal logic or intuitionistic or intermediate logic or any other. Because still there is many cases, I believe they are not difficult, but they are not easy also. It is of intermediate, more balanced complexity. For example, the unification type of KD. KD is the modal logic K plus the axiom diamond true. It corresponds to serial critical frames. Elementary unification, the unification type is not known. Or there is also very simple logic, the logic SL, or there is different name for it. It is K plus box P equivalent diamond P. It means that in critical frame, the accessibility relation is like a function. Each point possesses one and only one successor. So, for example, KD is included in SL. Therefore, immediately, the unification problem, the elementary unification problem for SL is NP complete. I have explained last week why for logic containing KD, the elementary unification problem is NP complete, because every variable free formula is either equivalent to true or to false. But the unification type of it, elementary unification type is unknown, elementary unification type is unknown, and I believe, and it is not, I don't find any way to attack the problem, but I believe it can be done by normal people. So we have seen what it means to be so L is a propositional logic, phi a formula, a unifier is a substitution which makes the formula the member of the logic. So provable if the logic is axiomatically presented, and valid if the logic is semantically presented. The formula is unitary if it possesses a minimal complete set of unifiers of cardinality 1. I remind what is a minimal complete set of unifiers. So it is a complete set of unifiers, and it satisfies some minimality property. What does it mean to be a complete set of unifiers? First, it is a set of unifiers of the formula, so every substitution that belongs to that set sigma is a unifier of the formula. It is complete because any unifier of the formula which does not belong to that set is an instance of a unifier of that set. And it is minimal because if you eliminate one unifier of sigma, it is not anymore complete. And a formula is unitary if it possesses such a minimal complete set of unifiers and it is of cardinality 1. The formula is finitary. We denote like this, 1 for unitary, omega for finitary. If it possesses still a minimal complete set, which is finite but not a single term. Infinitary, if it possesses a minimal complete set which is not finite. Unfortunately, I have no example to give about infinitary formula. And a formula is nullary if it does not possess any minimal complete set of unifiers. So, again, I remind that a logic is unitary if all its unifiable formulas are unitary. For example, classical logic, we have proved last week that classical logic is unitary by means of the Lovenheim substitution, showing that any unifiable formula is projective. It possesses a projective unifier, projectivity being an additional property of substitution. A logic is finitary if all unifiable formulas are finitary or unitary, and there exists a strictly finitary unifiable formula, for example, implicit logic and such modal logic. A logic is infinitary if all unifiable formulas are unitary, finitary, or infinitary, and there exists at least one formula which is infinitary. It is not known if there is such infinitary logic. Another problem, but I believe this one more complex. There is a book of Wojciech Zik. He is retired now, but he's still working, and he was actively working on the unification. He has a book, Unification Types in Non-Classical Logic. And he's explaining the construction of some very strange logic, which is, I can say, Polish logic. I have never seen it elsewhere. And it is, I recommend to read this book if you're interested in the problem. But it is not, for me, a natural logic. Maybe there is some motivation.
And this logic is
infinitary, yes.
And the finitary logics can be of some kinds. For some, the finite, the minimal complete sets are bounded by some cardinality, and in other logics they can be arbitrarily large. Are other examples of these two. finitely, but all minimal sets are at mode cardinality 10.
Yes, I understand your remark. It is a very good remark. But I have never seen. So in fact, there will be 10 finitary.
Yes, uniformly.
There is a bound on the
Yeah,
uniform
for
bound on the cardinality of minimal complete set of uniform.
Yes, it's deducible uniformly.
So K4, is it?
No, it is not. I don't know. I have not seen neither Balbiani nor someone else. I have not seen they discuss such a question, but I will be very surprised if it is true. I believe not. So it is a question also to prove that such modal logic, K4, S4, etc., that have been proved to be finitary, intuitionistic logic. Maybe it's not difficult. Okay, and what I was saying, nullary. And a logic is nullary if at least one unifiable formula is nullary. Okay, we have proved last time that classical propositional logic is unitary, and in fact we have proved that every unifiable formula is projective. Remind that in classical logic, a formula phi is projective if there is a unifier of that formula such that for all variable x occurring in the formula, this implication is a total loop. We have said that if two substitutions satisfy this condition, independently of the fact if they are unifier of phi or not, the composition of these two substitutions also satisfies this condition. And we have proved that if when a unifier sigma of the formula satisfies this condition for all variables, then it is the most general unifier of the formula. It does not give us that CPL is unitary, because it is to prove that CPL is unitary by means of such projective unifier, it is needed to show that every unifiable formula possesses a projective unifier. And we have proved it by saying the following. Suppose tau is an arbitrary unifier of a formula, an arbitrary of phi. Let sigma be the substitution which replaces the variable x by the so-called Lovenheim formula. There is a different way to introduce this substitution, but one way is this one. Then this substitution that we have constructed by means of an arbitrary unifier of the formula, we have shown last week that it is a projective unifier of the formula, and therefore it proves that every unifiable formula is projective. So CPL is unitary. Let us do the same for S5. So standard syntax of S5 and standard model. Models are partitions, that is to say, a non-empty set. Frames are partitions, non-empty set of possible words, and an equivalence relation on it. And models are determined by standard valuation. Truth conditions are, as usual, and validity in a frame. Truth in a model and validity in a model are as usual. There is a well-known and important and interesting properties of S5 that you already know probably. Every modal formula is equivalent to a formula of modal depth at most 1. And for example, such equivalence holds, and it is used such equivalence to show that every modal formula is equivalent to a modal formula of depth at most 1. And another property is that every variable free formula is either inconsistent or derivable. And it comes from the fact that S5 contains the axiom of D, the axiom of summing. So here let us prove that the proof that is written here, I will not follow this proof, I will do myself. I have given the reference of Zik, but he has a paper where he's talking about projective unifier in S5, but probably it was known before. So the proposition said that S5 unification is unitary. I have written elementary unification is unitary, but it can be proved that in fact also unification with parameters. So the proof on the slides is a little bit boring. I propose let phi be a unifiable formula. So let sigma be a unifier of it, arbitrary unifier, or tau. And let sigma be the following substitution. And it is very similar to the Lovenheim substitution that has been used just before to show that, to remind you that CPL is projective, is unitary. But here, of course, since the formula contains boxes, it is needed to adapt the Lovenheim, the so-called Lovenheim substitution to that case. Remark, so I define the substitution sigma, and I want to show that it is a most general unifier of phi, and in fact it is projective unifier. Since tau is a unifier of phi, then tau is also a unifier of box phi. By the rule of necessitation. This is a small remark. So there is some claim similar to what was happening for classical logic. The equivalence between sigma x and x is a consequence of box phi. Because if box phi is true, for example, if we are in the model, if box phi is true, that part disappears, and therefore sigma x becomes equivalent to x.
False.
Pardon?
If it is false, then that part is.
Yes, it is. Then sigma x is equivalent to tau x. And in fact, so this one is immediately giving us something which corresponds to the projectivity property. I have not said what it means for the formula to be S5 projective. It must be said what it means to be S5 projective, but it will correspond to that one. But in fact, it's for all formula psi constructed over the same variable as phi, and it is disprovable by induction on psi. Sigma psi is equivalent to psi. is a consequence of box phi. And as a consequence of diamond not phi, we have that sigma psi is equivalent to tau psi. It is by induction on psi. When psi is a variable, it is just what is written before. When psi, the main connective is a Boolean connective, it is by the induction hypothesis. And when psi is of the formula box psi prime, to prove this and this for box psi prime, we need to know that box phi implies box phi. It is explicit when we do in detail. We need to use this validity, which of course is derivable in S5, and this one, diamond not phi, implies box diamond not phi. In order to be able to apply, to use the induction hypothesis, if you want to prove for box psi prime, we will apply the induction hypothesis to psi prime, and to be able, we need such a validity. And for this reason, we can do because we are in S5, and these two formulas are S5 derivable. There are also K for phi derivable, but unfortunately, to prove that K for phi is unitary, it is much more difficult. Well, at least I don't know another simple proof. So we have this. And now, when we replace psi by phi, we have that box phi implies sigma phi, and diamond not phi implies sigma phi, because tau is a unifier of phi, and therefore that part disappears. And therefore, sigma phi is divided. To prove this one, we have just used the fact that tau is a unifier of phi. To prove this one, we have used the fact that box phi implies phi, and which is of course derivable in S5. And therefore, there is the three characteristic axioms of S5. They are exactly used at some specific place of the proof, showing that sigma is a unifier of phi. And this line shows that sigma is a projective unifier. I have not said what is projective, but it means to be a unifier satisfying this implication is derivable. And it can be proved in the same way as it has been proved in the classical logic, that if such a unifier is projective, then it is a most general unifier. So, S5 is unitary, and in fact, we said that S5 has projective unification, like classical logic, because every unifiable formula possesses a projective unifier. This proof cannot be repeated for K for phi, even for KD for phi, which is maybe the modal logic, the most close, the nearest to the S5, because for KD for phi we cannot use this one. It's not valid. And I don't know a proof of the unitary character of KD for phi which uses projectivity. Friday I will try to show that K for phi, in fact all extensions of K for phi and all its extensions have projective unification, but the proof is not so simple.
How many unitary logics are known at the moment?
All extensions of S5.
All extensions of this.
In his book, Wojciech Zik, he's addressing such problem, considering the lattice of all normal modal logic. In fact, also sub-lattice of this lattice, and he's trying to find interval in this lattice such that all modal logic in this interval are finitary or nullary, for example. He's giving such reason. But the unitary modal logic this one. And if we have the universal modality, of course. So if we extend the language with the universal modality, I will denote it like this. Now the frames, they are not partitions, they are just ordinary Kripke frame, just an accessibility relation with no specific properties. Syntax, truth conditions are defined as usual. The box is interpreted by means of this accessibility relation, and the universal box by means of the universal quantification over all possible words of the models. And in fact, this box is like a S5 modality. It can be interpreted, it corresponds to the universal relation between the possible words of the model, and therefore it is like an equivalence relation with exactly one equivalence class. And for example, interesting property of the universal modality is that if somewhere in the model box U phi is true, then box U phi is true everywhere else. And the same for the negation of it, which are also a typical property of S5 modalities. So we have seen that the unification problem for K plus the universal modality is elementary unification problem also with parameter is undecidable. And there is a simple proof that the unification problem in modal logic K, in fact in any normal modal logic, together with the universal modality, is unitary. I have written Bader and Ghilardi reference, but again, yes, this paper is very interesting because it is a good introduction to the problem. But again, I think it has been discussed before. So the proof again here is boring. So let us show here. In fact, it is exactly the same. Suppose that phi is a unifiable formula. In this language, with the box, the diamond, and the universal box and the universal diamond. And let tau be a unifier of that formula. I will construct by means of the unifier tau, which is arbitrary, another unifier sigma. But thanks to the universal box and the universal diamond. So it is exactly the same formula as before, except that the S5 box and the S5 diamond that were here and here, they are replaced by the corresponding universal modality. By the way, I am making this remark, but I don't know where it is used. Yes, it is used to show that sigma is more general than any other substitution. We need this. We need this to prove that sigma is more general than any other substitution. So it is important. And then I have just to replace here and there. Of course, here it must be replaced by the corresponding and the same here when we replace with the universal box and diamond. And it is like this because this universal box and diamond implies, we are also using that box C, box universal C implies box C, plus the S5 axiom for the universal box. They are all these axioms are needed to prove that all these derivable formula. And it shows that modal logic K extended with the universal modality is unitary. Every unifiable formula possesses a projective unifier and therefore possesses a most general unifier. In fact, here I can say every normal modal logic together containing the universal modality is of that kind. So when there is the universal modality, for the unification type, it is relatively simple. Here there is a remark, but maybe just for the happy few, or for further investigation if you want. We have proved that unification in S5 and K with the universal modality, in fact, all modal logic L with the universal modality, is unitary. And to prove it, we have in fact proved that unification in this logic is projective. That is to say, if a formula phi is unifiable, then it possesses a unifier which satisfies the projective condition. And to satisfy the projective condition for a unifier, we have seen how it shows, it can be proved that this unifier, sigma, is the most general unifier, and then it implies unitary of the unification problem. But to be unitary and to have a projective unification problem, it is a different property. To have a projective unification problem implies the logic is unitary, but not the converse, because there is example. Yes, the example is next. Yes. If unification is projective, then unification is unitary, but the converse is not true. There is such exotic modal logic for which unification is unitary, but not. I was not remembering this one, so it is another example. I don't know if for you it is exotic, but if someone is asking me to write the Schreiber-Chick axiom, I will not be able. Okay, this is just.
Unification is unitary but not projective.
Yes, so it shows that to be unitary or to be projective are different things. To be projective is stronger. S4 but to genotype. How much time there is?
I think we have about 10 minutes.
10 minutes. Okay. Okay, 10 minutes, there is not enough time to do something. Just to mention what we will do Friday. Yes, there is a quite important number of results obtained mainly by Wojciech Zik, Wośtilak, a colleague of him, and some students of them, to consider intuitionistic logic and intermediate logic. So this is the definition of intuitionistic logic. For example, one result which is quite interesting is that the Gödel-Demet logic LC, which is intuitionistic propositional logic plus P implies Q or Q implies P as a new axiom, and which correspond in the Kripke frame to the linearity property of the ordering relation, is unitary, and all its extensions are also unitary. But the extension of this logic, they are known also, and they are all of them unitary. So I will try to prove this one. Let me try. I'm not sure it will be. We will do this one. We will consider K4. I will sketch the proof of Silvio-Ghilardi showing that K4 is finitary for elementary and unification with parameters. And we will prove that modal logic K is unary. And we will prove that modal logics like K, all normal extensions of K for 5 are unitary. And maybe also some other, I don't know, I will see. But each time that it will be a different proof. So for this way, in this way, it is interesting to see a different proof to show the unification type.
So what I remember about the difference logic, it is still unknown, right?
The difference logic, I have not studied
Okay.
weak K4 plus symmetry. Weak conductivity plus symmetry.
Might be.
I don't know. Maybe we will do Friday. Okay. If there is question, I will be happy to answer.
You have mentioned a very exotic logic,
Which one?
Polish logic.
S1. No, it's not Polish. S4.2 plus
It's not exotic. It's well known.
Yes, of course.
Okay. I was wondering if it was used only for proof of something, or it's just useful for some other things. Is it used somewhere else?
I don't know.
Okay, only for proof.
But Professor Shetman can give answer about it.
What was the question?
Where can you find this logic besides the usage in this proof?
Oh,
Is it useful for something else? Or
it is useful for something else.
Okay.
It is, yes.
Okay.
It is sort of Medvedev, yes.
Okay.
Yes. Like Medvedev, but with the top.
So it's recursive geometry, no infinite parts, and dot 2 is
Confluence. Jump confluence.
It is the logic of all cubes, of all, actually.
Okay. Focus. Okay.
full cubes.
Full cubes. Yes. Without finite, not all finite. All finite.
Not topless.
Yes.